Okay, one of the last big topics for college algebra and probably easier than the log stuff is matrices. Um, so it's not pronounced matrices, it's matrices. Um, we're going to look at the matrix representation of a system of linear equations, and then later on we'll look at what are called row operations, and then eventually um, reduced row echelon form as a method of solving a system of linear equations. Uh, so here we're going to practice given a system of equations. So I have a system of two equations and two unknowns. So this is from section 8.1. You could solve by graphing, by substitution, or by elimination method. And the solution is going to represent a point where the two lines intersect. Maybe the two lines are the same, or maybe if there's no solution, if the lines are parallel, they are not going to cross. Another way we can represent this as instead of a system, we can represent it as a matrix. So I said matrix, but it should say matrix. I'll fix the spelling here in just a second. And what it allows us to do is it's a little bit of a simplification. So we're just going to write the coefficients of the variables. So you're going to have an x column, a y column, and then you're going to have the constants on the other side. So for that first equation, we'll have 2, 5, and then I draw this vertical line to indicate the equal sign. So this is 2x plus 5y equals 7. The bottom will be 3x minus 11y equals 8. So we do not write the variables, and it has some advantages, especially if we want to use computers to help us solve this. If you're planning on taking finite math, or I think even the business math will use some matrices, and they do have some applications. If you're going further in math, then you'll certainly see them in linear algebra, and you can also use them in Calc 3 if you're going to solve what are called Lagrange multipliers. Some fun stuff. Anyways, so there's a system of two equations and two unknowns. We'll give you a system of three equations and three unknowns. You can do as many equations and unknowns as you desire. Notice that the second two equations in this system here are missing one of the variables. So if it's missing one of the variables, we're going to have to put a placeholder 0 when we put it in the matrix form. Alright, so then I corrected my spelling of matrix. Alright, so the coefficients go 5, negative 1, and then the constant 0. And then constants 1, 1, coefficients 1, 1, and then there's no z, so we have a placeholder 0, equals 5, and then 2, and then no y terms, so 2x, 0y minus 3, and that equals 2. And that's our matrix representation. So then we're going to be able to learn a way of solving a system of linear equations using the matrix. Okay, now when we're doing matrices and we're eventually want to do Gauss-Jordan elimination, there's three row operations that we can do. The first is you can interchange any two rows. So I realize I'm using the wrong interchange. So let's try this again. So we will try to use correct spelling. So you can enter, and it looks like we're having trouble writing. Alright, here we go. Not everything is registering. Alright, there we go. You can interchange any two rows, so that means we can switch them. That's all it means. So we'll take a look at what that looks like if I do it with a system of equations. Okay, so if I only got two, it means I can switch them. If I have three, then I can switch any two of them. So we can choose which one we write first, second, and last if there's three of them. Or we can, if there's two of them, we can choose who's on top. That's all it's saying. We can interchange two rows. With matrices, it just means we can switch the rows. we switch the rows. So we have, those are our rows, and then above are columns. Okay. Now let's look at the second row operation we're allowed to do. And we're allowed to multiply a row by a non-zero number or non-zero constant. So let's take a system of equations, and maybe we're wanting to solve this by elimination method. So we could either eliminate the x or the y. It doesn't matter. Maybe we'll eliminate the x's, so we'd want to multiply the top equation by 2. So this row operation says we can multiply the top equation by 2. 2 is non-zero. And then we can rewrite our system of equations just like a matrix just as is, and then we continue on the process. Now if we do with the matrix, the only thing that's different here is kind of the notation. So what I'm going to say is 2 times row 1, so that'd be the top row. So I'm going to say 2 times row 1, and then I'm going to use an arrow to point that becomes the new row 1. So sometimes when we're doing the operation we say little r, and then when we say this is what it's going to become, we use big R to be the final. And all we do is multiply the top row by 2. So 6, -2, and 16. And the rest of the matrix is the same. Now the last row operation might be a little bit tricky. It'll take a little bit of time to get used to, but it's not bad. And it says you can add a constant multiple of one row to another row to replace it. So basically we can multiply the top row by 2 and then add it to the second row, and that would replace the second row. So we'll see what it looks like with just a system of equations, and it's something we do kind of with the elimination method, but maybe we don't quite write it the same way. So let's say we're looking at the same system of equations that we looked at on the previous example, and we just multiplied the top by 2, but now we can actually multiply the top equation by 2 and then add it to the bottom equation. Okay. The top equation is unchanged, so it didn't change. Now we usually wouldn't write it this way. We would just find our answer for one of our variables, and then we'd plug it back into this equation to find the missing piece. But it's unchanged. All right. So now what's happening is I'm doing 2 times 3. So we're doing 2 times 3x, and then we're going to add it to that -6x, and that's going to give me 0x, and then I'm going to take 2 and I'm going to multiply by the -y, and then I'm going to add it to the 3y in the equation beneath that, and that's going to give me just 1y. Okay, then I'm going to take 2 and multiply it by 8, and then I'm going to add that to the 12, and that's going to give me I believe 28 if I do the addition correctly. Okay, and that's all we're doing with solving a system of equations. Now we would say, oh well, y is equal to 28, and then I could go back and I could substitute it in for y and then solve for x. So this equation wasn't changed, it was the second equation that was changed. Okay, so let's erase all this, and then we'll do our matrix example. And the matrix example is going to work out very similarly. So we'll write our matrix in, but the notation's a little bit different. Okay, so what we're going to do is we're going to take row 1, I'm going to multiply it by 2, so there's where the 2r1 comes from. I'm going to add it to row 2, and that's going to become the new row 2. Okay, so the top is unchanged. Okay, the top is unchanged, but if I do the top row, which is 2, and then we're going to multiply it by 3, and I'm going to add it to the -6 down below, so we're kind of adding these, 2 times 3 plus negative 6. That's going to give me the 0 here. And then what I'm going to do is 2 times the negative 1. And I'm going to add that to 3. And that's going to give me my answer there. Okay, so let me erase some of this stuff. That's the problem. It gets a little bit cluttered if we try to write everything out here. Okay. And then finally we'll do 2 times 8, and we'll add that to 12. And that will not give us 8 if we can add correctly. How much was that? It was 28. Okay? And from here, I can read that my answer is y is 28, and then I could go back and plug into this equation, which is actually that one. So that's what's going to end up being called back substitution later on.